Hello and welcome to this video where today we're going to look at projectiles. So we're looking at objects that move only under the influence of gravity. So we're not thinking about objects that have engines or rockets or anything like that, simply something that's just been thrown. Now before we think about how you would calculate, for example, how far they've gone, how high they travel, just one real quick aside, because we're thinking about the force of gravity on an object, it's probably a good idea to actually define what that force is. So the force acting on an object due to gravity is its weight. So this is how we would calculate it, where W is the weight of our object, and that's given in newtons. M is the mass of our object. That isn't a force, and that's a very common mistake. Mass is quite simply the amount of matter that's contained inside an object. You can't really change this, so if you've got a plane, it's made up of a certain number of atoms, and you can't really get rid of those atoms, really. So the mass generally remains constant, and mass, as we know, is measured in kilograms. And then G, now this is related to how strong the gravitational field is, because this is basically it's either the acceleration due to gravity or the gravitational field strength, and the gravitational field strength is potentially the best thing to think about. So that's a gravitational field strength. Now, gravitational field strength is measured in newtons per kilogram. So basically what this number tells you is it tells you how many newtons of force an object experiences for every kilogram of mass it has. This again is generally a constant for a certain planet. So for the Earth, for example, the Earth has a gravitational field strength of approximately 9.81 newtons per kilogram. Now you can also define G to be as I said before, as the acceleration due to gravity, and if we do that, then actually you end up with exactly the same number, so 9.81 meters per second squared. So basically every object when it's dropped accelerates at 9.81 meters per second squared, provided that there's no things like air resistance and things like that going on. So if you took, for example, a feather and a hammer, then if there was no air, if we were in a vacuum, then both of those would accelerate at 9.81 meters per second squared. So they both fall down together. So just to reiterate what a projectile is, this is something that's not got an engine, so it's something that's where the only force acting on it is its weight. For example, if you throw a ball straight upwards, that would be a projectile because the only force acting on it is the weight pulling it downwards. If you fire a bullet from a gun, so for example the bullet comes out of the gun, it will gradually fall down like this. That's not a very good drawing, but it will gradually fall down because at any point, so this point here, the only force acting on it is its weight downwards. There will be forces acting on it to make it go this way, but we're only thinking about the actual motion once it's kind of been pushed out of the gun. So that would just be the weight downwards. And as we've said, a rocket isn't a projectile because the gravity isn't the only force that acts on that object. So often when we're thinking about projectiles, the thing that we really want to work out is we want to work out, for example, how long they're in the air, how far they fly through the air, that type of thing. And for this, we can use those equations of motion that we saw before that are often known as Suvat equations. The reason we can do this is because the acceleration is a constant. The only acceleration that these projectile objects experience is the acceleration due to gravity, which is straight downwards, and it's always the same. So it's always 9.81 meters per second squared all the time. So because we have constant acceleration, we can use these equations of motion. Now there's one huge key idea with projectiles. This is potentially the biggest idea at all to do with projectiles. And that's that we can split up the motion in the vertical plane, so the up and down plane, with the horizontal plane. They're completely independent of each other. So you can, let's imagine, for example, that we had a cannon, and the cannon fired a cannonball out, and it's on top of a cliff, so it makes that type of shape. And at exactly the same time, somebody drops basically the same kind of cannonball off this cliff. And what we'll see is after a couple of seconds, this thing's falling down and this thing's accelerated, but because they both accelerate downwards and only downwards, so there's no force horizontally or any other force, because they both accelerate downwards with the same acceleration, then they'll fall at the same rate. So let's imagine that each of these dots took 1 second. So we had 1 second, 2 seconds, 3 seconds, 4 seconds. After 5 seconds, the cannonball that was just dropped is here. And then if we draw a line across like this, after exactly the same amount of time, this one is in exactly the same place. It doesn't matter at all that it's also travelling in this direction. The only reason it makes this shape is because it's travelling downwards, so it's accelerating downwards, but it's also moving with a constant velocity in that direction. So we've got acceleration downwards and zero acceleration across, and we can split this motion up into two. And because of that, we can then work out, for example, how far this thing's going to go. Now, just before we do that, there are a couple of key terms that we need to think about. If we're asked for the range of a projectile, what that basically means it means that it's the horizontal distance travelled before, for example, it hits the floor. So if we're thinking about the range of this red projectile, that's the distance from there to there. So the range would be how many meters that distance there is. The time of flight is quite obvious. It's basically how long the object is in the air for. Another thing to know is that as this thing flies through the air, it makes a characteristic kind of curve, and the curve's always the same. It's always a parabola. So here we've got kind of like part of a parabola. If we'd have fired it up and downwards, it would have also made a parabola. So it's a parabolic shape, and that's really, really important. So we're going to have a look at how you answer these projectile questions. The very first thing we do is we split the motion up into two directions, vertically upwards and horizontally. So it's almost like we're kind of resolving and then looking at each situation completely differently. We can use our Suvat equations for each direction separately. So what we would do is we would basically start off by writing Suvat vertically and Suvat horizontally. We'd look at what we want to calculate, what we've got, and then basically we'd try and work out what we need. And very often what we have to do is we have to work out, for example, the time from the vertical components, so we know how long it was in the air for, and then use that in the horizontal motion, for example, to work out how far the thing's gone, as we'll see in a second. So let's have a try at this. So here what we've got is we've got a bullet, and it's shot out of a gun horizontally at 500 meters per second, and it's shot from a gun which is 1.5 meters above the ground. We want to know the range of the bullet. So basically what it's doing is the bullet starts off in the gun, it gets shot outwards horizontally, and it will fall down like that, and it'll make our parabola shape, and it will eventually hit the floor. The distance up here, so the height that it was shot from was 1.5 meters, and it was shot with a horizontal velocity of 500 meters per second, like that. So that's basically what's going on. We want to know how far this thing travelled. So to do that, I'm going to do the two things that I said. First of all, I'm just going to write down Suvat and look at what I've got. So we'll have a look horizontally. So S, U, V, A, and T. So horizontal displacement is actually the thing that I want to know. So in the end, that's what I'd like to know. So I need to use this thing, these horizontal quantities in order to work out the horizontal distance or the range. I know the starting or the initial velocity because it tells me in the question up here. Because it's horizontal and this is horizontal motion, that's 500 meters per second. I also know, because I know that the only force acting on this object is downwards, that its horizontal velocity is going to stay the same all the time. So its final velocity is also 500 meters per second. And again, because there's no force acting on it in the horizontal direction, acceleration is 0 meters per second. And time, well, I don't know anything about time, so again, that's an unknown thing. So if I want to know the range or the distance that this travels, I need to use an equation. So, for example, S is the thing that I want to know. I know U, I know A because it's 0, and I know T. So I could use this equation here. So I could use my Suvat equation, S equals UT plus a half AT squared. So I could use that equation, but for that I'd need to know T. Now, if you're the observant amongst you will notice that if the acceleration is 0, this whole term just becomes 0. So actually I end up with the displacement is equal to the initial velocity multiplied by the time. If you rearrange that, you actually get speed is distance over time. So actually for the horizontal motion, you can just use speed is distance over time and rearrange that to get basically the displacement is the initial velocity multiplied by the time. You don't really have to think about this acceleration at all. If it helps, just use your Suvat equations and you just put acceleration is equal to 0. So if I look at this, this is what I want to know. I know the initial velocity, I don't know the time, and I have no way of finding the time from this. But what I'll do is I'll do exactly what I said before, and we'll write down Suvat in a vertical motion, so Suvat. So what I'm going to have this time is a completely different set of numbers. So displacement upwards. Well, what this is doing is it's starting off up here, and it's travelling downwards. So I'm going to say it's starting off at 0 meters and it travels downwards. Now, because I'm thinking of this thing going, the upwards thing being positive, because these things are vectors, my displacement would actually be minus 1.5 meters. Like that, because it's when it finishes, it's gone from 0 to 1.5, so it's gone down 1.5 meters. So the displacement is minus 1.5 meters. Its initial velocity, when it's just about to fall down, well, its initial velocity is all horizontal, so it doesn't have any velocity in a downwards direction. So initially, 0 meters per second is its velocity. Its final velocity downwards, I don't know, so I'll leave that one. Its acceleration, well, I know that. Its acceleration is minus 9.81 meters per second squared, and it's minus again because the acceleration is downwards, whereas we're thinking about motion upwards. And the time, again, is something I don't know. But if I can work the time out here, obviously that time is the same as this time. So let's have a look at this equation. I know the displacement, I know the initial velocity, I know the acceleration, and I want to know the time. So again, if I use this equation, if I use our S equals ut plus half at squared, I could use this equation and I can work out what t is. So I put all my numbers in. Displacement is minus 1.5 meters. That's equal to the initial velocity, which is 0. So 0 times t is 0. So that kind of is 0. So I've just got this bit. Sorry, I missed out half there. So s equals ut plus a half at squared. So that's 0. So I've got plus a half times the acceleration, which is minus 9.81. 9.81 multiplied by time squared, which I don't, which is the thing that I want to know. So if I rearrange this thing over here, so let's start off up here. If I'm going to multiply, basically I multiply by 2, so I end up with minus 3.0 is equal to minus 9.81 t squared. So now it's just a matter of doing a bit of math. So t squared is equal to minus 9.81, sorry, is equal to minus 3.0 over minus 9.81. And if I do that on my calculator, I end up with something in the region of 0.3058 and if I take the square root of both sides, I end up with t being equal to 0.5530, etc. Now, I'd keep that in my calculator because that's a more accurate answer. But basically, I know it takes 0.55 seconds to go from here down to the floor. So it's also going to take, but the whole motion is like that, so it takes 0.55 seconds to get from there to there. So now I know that this is approximately 0.55 seconds, and so is this. They're the same number. So what I can do is I now know the initial velocity, 500 meters per second horizontally, and the time, which is 0.55. So if I now use this equation, so if I now, again, go back to looking at the horizontal motion, the displacement is equal to the initial velocity, 500, multiplied by the 0.5530, which basically in the end gives me approximately, well, at least to three significant figures, it gives me 277 meters. So this bullet will travel 277 meters before it drops the 1.5 meters and hits the floor. So that's the starting look at projectiles. What we're going to do is in the next video we'll take a little bit more time and we'll have a look at what happens when we have projectiles that are not projected horizontally but actually they're projected at an angle, so they go up and then back down again. But for the time being, that's it from me, and thank you very much for watching.